Okay, in this video we're going to look at distance time graphs. So these distance time graphs are used to show the speed or the velocity of an object. So it still kind of ties in with velocity. And if you haven't watched that video, I recommend you might want to have a look at that one first. Alright, so let's have a look. Alright, oh, sorry, jumping a bit too far ahead there. So this is an example of a distance time graph here. Alright, and if you have a little bit of a look at it, you've got distance along the y-axis, along the left-hand side here, and time along the bottom. So let's have a quick look at what these lines actually represent. So let's start with this flat line here. If we've got a flat line, what does that mean? Well, it means my distance over here isn't changing as time is ticking along. So imagine if you or I were running a race. What's happened is I've gotten to, now this might be, if this is meters, I've gotten to about 2.5 meters, and then my distance from the start line isn't changing. So what does that mean? Well, I must have stopped. So I'm not increasing, I'm not getting any further away from the start line. I must be standing still or have come to a stop. Alright, so a flat line on a distance time graph means the object is stationary, or it has stopped. Now if we look at a sloped line, like the start of this the red part of the graph here, it's an object travelling at a constant speed. If we look at the green one here too, it's also travelling at a constant speed, but it's travelling slightly faster. Let's just think about that for a sec. So the green one here is going up roughly 2 meters, or just over 2 meters every time we go across 1 second. So we go across 1, and we've gone up about 2 and a bit meters there. And after another second, we've gone up another 2 and a bit meters there. So the slope is showing, we're constantly getting further away as time ticks along. So we're traveling at a constant speed. What does it mean if the line slopes down, like at the end of the red part of the graph here? Well, it actually means, so if this was me running at a constant speed and then I stop, and then the line slopes down, so my distance from the start line was 2.5 meters away from the start line, not very far, but then actually I start to get closer again, I get closer to 0 again. So this is actually a constant speed, but it's something that's traveling backwards, or traveling back to its point of origin. Now a curved line here, curving up, is essentially, it's something that's getting even faster. It's getting steeper and steeper, so it shows what we call acceleration. So a curved line curving up is acceleration. Now we'll come back to that, but we're going to try and link it, or look at that we're going to try and tie that together to our equation that we've been using so far. So using our triangle here, we've said that velocity, I'm just going to change my color pen, that velocity here is equal to distance divided by time. Now, if you're a budding mathematician, you'll know that the slope of a graph, of a line on a graph like this, the slope is equal to the rise, or the change in the y-axis, over the run. So what do we mean by rise over run? How much it goes up for every bit that it goes across. So like we said with the green one here, it's rising by about 2.5 or 2 and a bit meters for every second that we go across. Now if we look at the rise over the run, so let's take a look at this green line for instance. Let's take a nice clean point here where it crosses, it intersects with the grid we've got. So we've gone up, our rise, we've gone up, right? How many meters is this? 1, 2, 3, 4, 5, 6, 7. We've risen by 7 meters, and we've gone across our run. It's taken us 3 seconds to go, to reach those 7 meters. So my rise over my run, well, the rise, what kind of value is that? Well, it's a distance. And the run, what kind of value is that? Well, the run across here, well, that's a time. So if the slope of my graph is rise over run, and the rise is distance, and the run is time. Well, then my slope is distance divided by time, and well, we know distance divided by time is actually the speed. So the slope of the graph actually equals our speed or velocity. So what that means is the steeper the slope, like the green line here, the faster it's travelling. It's going 7 meters in 3 seconds. Whereas you look at my red line here, and it's only gone 2.5 meters in 3 seconds. So it's going a lot slower. If we look at our curved line, I'm just going to clear all of that, you can see the slope. Imagine the slope here. I'll just change my colour pen again. Let's grab sort of a highlighter. At the start here, you can imagine the slope is fairly flat. And as we get up towards this end, the slope is getting much steeper. If we look at a small section of it and kind of imagine it's flat or straight, you can see here the slope is a lot flatter and here it's getting a lot steeper. So that the steepness or the gradient, the slope of the graph is increasing, which means the speed is increasing. It's accelerating or it's speeding up. Now one line that we haven't shown on this graph, and I'll draw that one in quickly, is a line that would look like this, that would curve over like this. So it's a curve, but it curves the other way. And this one's actually slowing down. You can see the graph starts off steeper, and it gets flatter and flatter and flatter, and it slows down. And in fact, if it flattens completely off, so if it gets flat like my one here, well, remember a flat line is stationary, it's stopped. So this one's slowed down or decelerated right down until eventually it's stopped. Cool, so let's have a look. Let's apply this to an actual question, see what you might actually get asked and how you can use this to tackle an exam question. So here we go. A woman drives her tractor down a sandy beach to pick up her friend's boat. The distance time graph below shows part of the journey. Use the information from the graph to calculate the average speed of the tractor during the 90 seconds. So if we have a look here, firstly, let's have a look at our graph before we actually answer any of the questions. So we've got a section down the bottom here, section A, and it's curving up slightly. So we know at this part here, during section A, it's accelerating, it's increasing, it's getting faster. During section B, we've got a flat line here, a straight line that's, sloping upwards. So we know we've got a constant speed. So this is the tractor probably speeding up initially until it reaches a certain, a particular speed, and then it travels at a constant speed, travels there at a constant speed. So to work out the average speed, we don't have to worry too much about any of that. So the average speed, it doesn't matter if it was going a little bit slower at the beginning here and faster towards the end. We're just going to work out the total, or average speed. We take the velocity equals the total distance divided by the total time. So we can say in this case, I'll just get rid of that, we could say the distance that's travelled in this case is, if we have a look, we've gone from 0 to 600 up here. So from 0 meters to 600, we've gone 600 meters. And so put in meters there. And we've done that in here, we've got 90 seconds. So 600 divided by 90 seconds there. If we plug that into a calculator, we get an answer which is I'll just double check that, 600 divided by 90, being a bit lazy, yep, now on your calculator will say 6666, we're just going to round that to say like 6.67 meters per second. Okay, so we can just round that up a little bit, so we've got 6.67 meters per second, and they were actually nice enough to even give us the unit here. So guys, really important that you do the formula, show you're working, give us the answer and the unit. There can be marks for all those sorts of things, or what might happen is if you make a mistake you might at least still get some marks for it. Okay, so this is the average speed. Obviously it would have been going a little bit slower at the very start here and a little bit faster it got up to speed towards the end. But the average speed, just the total distance divided by the total time. Alright, so let's get on to the next part. So look at part B. Describe the motion of the tractor in section B and explain what this tells us about the forces acting on the tractor during this time. So if we look at section B, was where it was a straight line with a slope like this. So that tells us it was travelling at a constant speed. So we know it's travelling at a constant speed. So saying it's travelling, now you want to write full sentences, I'm just, in the video it's a little bit tricky for me to write on the screen, but so describing the motion would simply be saying it's travelling at a constant speed. Explain what this tells us about the forces. Well, this actually relates to our last couple of videos where we looked at forces and how that affects motion. If something's travelling at a constant speed, the forces acting on it must be balanced. Now there are a couple of ways you could say this. So they would have accepted it that, because it's travelling at a constant speed, the forces must be balanced. They would have also accepted if you said the net force or total force acting on it must be 0. The one thing they wouldn't accept is if you just said the forces must be equal. They would actually accept if you said the forces acting on it are equal and opposite, but they wouldn't just accept equal. And the reason for that is, let's pretend there are two forces acting on it. Well, if they're equal, they could actually be both pushing in the same direction, in which case they'd be helping each other out. We could add them together, and that would obviously give us a net force pushing it in one direction. So they want you to say, and the best probably option is just to go with the term balanced. The forces acting on it must be balanced, otherwise it would accelerate, speed up or slow down. Its motion would change. Alright, so let's have a look at C here. C is your sort of tricky part of this question, and it is a little bit tricky. The total mass of the tractor and driver is 1,660 kg. Calculate the speed of the tractor at the end of section A, and then calculate the net force acting on the tractor during section A of the graph. Alright, so let's calculate the speed of the tractor at the end of section A. So if we look at the end of section A, if we have here a look at the end of section A, we've got during section A it's speeding up, speeding up, speeding up, and at the end of section A it's now reached a constant speed which it continues at during section B. So it would be impossible on our graph to kind of determine the speed just from a point. But what we can do is we can say at the end of section A it's reached its kind of maximum speed, and it's obviously carried on at that speed for the rest of section B. So it may seem odd, but it actually means that the speed during section B is the maximum speed it's that speed we've reached at the end of section A. So to work out the speed on our distance time graph here, well, we just take the rise over the run. Remember the slope that we reach here, the slope is the rise over the run. So we're going to take the rise, which is our distance, divided by the run, which is our time. So we go here, the velocity equals, we've got the rise, so from 120 to 600. So how much have we gone up there by? Well, 600 take away, we've gone up by 480 is my rise. Now remember, if we're working out the slope for this part, we wouldn't start down the bottom here. So we've gone up by 400, and so that's meters. And we've gone across by here 60 seconds. We've gone across by 60 seconds. So that equals, let's have a look, 480 divided by 60, we've got 8 meters per second. So during section A, it would have started probably, if this is completely flat at the beginning here, it started off at 0 meters per second and accelerated, got faster until it reached the slope here, during section B. So during A, the final speed reached at the end of section A is 8 meters per second. It's actually the slope here of section B. Alright, so a little bit tricky there because lots of students would have taken, the rise of the run of section A, and it's just tricky in terms of the wording. So it asks you, it asked us actually here, if we go back to the question, it asked us to calculate the speed of the tractor at the end of section A. So that's actually, the slope we've reached during section B then. We then have been asked to calculate the net force acting on the tractor during this section, and we're going to actually answer that in one of the next videos. So what we can actually do is we're going to work out the acceleration, and I'll show you how to do that in the next video, and what we can then do is we can say that the force is equal to, we've done that one before, mass times acceleration. So that was from one of our previous videos. But to do that, we need to work out the acceleration here. Alright, so we'll go on to the next video and basically start to have a look at acceleration.